So good evening, good morning, or good afternoon, depends where you are. So hello everyone, welcome to INRS Talks, Connect the World. My name is Rong Chen from Huazhong University of Science and Technology, and I'm going to moderate the talk tonight. Well, as you see, we have a wonderful March session. Last week, we have INRS Young Scientist Awardee talks from Professor Jonathan Rivener from Northwestern University and Professor Changyong Chao from Case Western. And today we are very fortunate to have Professor Federico Rosei from INRS Canada. And also we have a strong panelist team, Professor Francisco Stalachi from EPFL and Professor Rusen Yang from Xidian University, as well as our ex-challenger Shi Yuwei from Australia National University. So first, let me introduce Professor Federico Rosei, who is currently a full professor and former director at INRS Center for Energy, Materials, and Telecommunications in Canada, Quebec City. So since January 2014, Professor Rosei holds the UNESCO Chair in Materials and Technology for Energy Conversion, Saving, and Storage. So Dr. Rosei's research interests focus on structure-property relationships in nanomaterials and their use as building blocks in emerging technologies. He has published over 400 articles in prestigious international journals and has been invited to talks over 300 international conferences, even over 200 seminars, colloquiums, and quite a lot of the lectures and public lectures in 48 countries all over the world. His publication has been cited over 20,000 times, and his H index is 75. Professor Rosei is a fellow of numerous prestigious national and international societies, including Royal Society of Canada, the European Academy of Sciences, APS, AAAS, etc. And Professor Rosei has also received several awards and honors. There's a long list, and I'm not going to go through all of those. So without further ado, let me welcome Professor Rosei to the stage for his talk tonight, Multifunctional Materials for Emerging Technologies. So Professor Rosei, please.
So thank you very much. It's a great honor for me to be here with you today. Thank you for the introduction, and I'd like to thank Professor Zhang for the invitation. So I will hopefully be able to share my screen. Let's see. Let's see. Can you see the screen?
Yes.
Yeah.
Yes. Mm-hmm.
Okay, perfect. All right. So go in presentation mode. All right. No, it didn't go yet. Now, yes, finally. Okay, so I started my career as a sort of independent scientist as an academic about 21 years ago. In 2 months, it will be exactly 21 years. And originally, I was trained in physics, and I was studying very fundamental properties of materials, looking mostly at surfaces and interfaces, and trying to understand how the structure, if you like, the morphology and composition of a material determines its properties and functionalities. Over time, I started working on more applied topics and using these materials, particularly nanoscale materials, as building blocks in emerging technologies. So we branched out in several directions, looking at biomedical materials as well as organic electronics and aerospace materials. And I guess over the past 10, 15 years, we shifted our focus to study mostly materials for renewable energy technologies. And you'll see in a moment why there has been this shift. So a few years ago, the United Nations defined the concept of sustainable development, and they also defined the 17 Sustainable Development Goals. These are sort of grand challenges that need to be urgently addressed if we're going to chart a course of towards sustainable development. In other words, for a peaceful coexistence of all living species on planet Earth. I circled in blue the ones that we as scientists, as academics, can credibly address, at least in my opinion. So that would be number 3, good health and well-being. Number 4, of course, quality education. Number 6, clean water and sanitation. Number 7, affordable and clean energy. Number 9, industry, innovation, and infrastructure. Number 11, sustainable cities and communities. Number 12, responsible consumption and production. And number 13, climate action. Now, I have an issue with the 17 Sustainable Development Goals in the sense that 17 is a very large number. When you have too many priorities, in some ways, it's like not having any priority at all. So I think if we really want to take this notion of sustainable development seriously, then we have to sort of decide what is really urgent and what is perhaps not so critical at this time, or maybe create a hierarchy within these goals. So if I had to pick one urgent, critical challenge that we need to address, it would be energy. These two graphs are taken from a paper published in Physics Today about 15, 16 years ago. And what's remarkable is that they're still incredibly quite accurate. So the predictions were spot on, if you like. So on the left, you see the breakdown of the types of energy we use. Today, in 2023, about 80 to 85% of the energy sources we use on a planetary scale are made up of fossil fuels: oil, coal, natural gas. What we know about fossil fuels is that they're highly polluting. They cause substantial greenhouse gas emissions. And of course, they're not renewable, at least not on a time scale that is meaningful for us. If you like, over a period of millions of years, they will be renewable, but obviously we need something that is more manageable in the short term. A few percent is nuclear. Of course, nuclear is less and less popular for psychological reasons, shall we say. A couple of percent is hydroelectric, and then everything else was generically labeled as biomass and other. Of course, these would be the renewables besides hydroelectric, which is obviously also renewable. There's geothermal, tidal power, wind power, and clearly solar. Solar is actually a very interesting case because the worldwide use of solar energy, of direct conversion of solar energy into another usable form, is only about 1%, which essentially means it's negligible. Now, that's the bad news. The good news is that, well, if it's so low, it can only get better. So let's be hopeful that we can increase the percentage of solar, and also that we can increase the relative percentage of all the other renewables with respect to fossil fuels. Now, if you notice, the renewables have been growing in use, but they've been growing in absolute numbers, but not in percentage. And this is a critical aspect I will discuss in a moment. I also wanted to mention about solar that the sun sends towards our planet in 1 year enough energy to power the whole world for in 1 hour, it sends towards our planet enough energy to power the whole world for 1 year. So In a theoretical concept, 1 hour of sunlight would be sufficient for a year, and yet we only use 1%. Now let's look at why the percentages have not changed even though the numbers have increased. Well, that's entirely due to population growth. You can see on the right-hand side this other graph, which plots world population as a function of time for the past about 800 something years. We have reached 8 billion people on this planet, and historically we've never had that many people, humans. Now, if we go back in time a few hundred years, we were much, much smaller in world population. In fact, world population was hardly growing at all, more or less constant, growing very, very slowly for hundreds, maybe even thousands of years. And this happened until the 1800s, the era that is generally referred to as the Industrial Revolution. And that's when he started using heavy machinery. But if you think about it, the fuel that powered the Industrial Revolution is coal. Before that, we were mostly burning wood, essentially. And so in a sense, we can sort of label everything that happened since the 1800s the energy revolution. Coal is the first fossil fuel that humanity used on a large scale. Then we started using, of course, also natural gas and oil. We've already covered the sort of drawbacks of fossil fuels. They're not renewable and they're highly polluting, but they also have some tremendous advantages. One huge advantage is that they're easy to transport. Another advantage is that they have a very high energy density, which means that from a small volume of fossil fuels, I can harness a lot of power. Another advantage for a long time has been that they were low cost. So if you put all these advantages together, it's not surprising that we have become so dependent on fossil fuels, and they have enabled so many technologies that we take for granted, at least in sort of rich countries in the world. But at the same time, they have directly or indirectly prompted many other advances, including medical advances, so that the average lifespan of humans in rich countries, in many countries, all across Europe, North America, as well as many countries in Asia, including China, it's now over 80 years. And this was not true just a few generations ago. If you go back about 100 years, the typical lifespan of humans would not exceed 60. And this also contributed to the increase in world population. Now, this is a huge component of the sustainability challenge, because you can immediately realize that when there's more people, they obviously need more energy, they need more food, they need more jobs, and more healthcare and clean water, and they produce more waste, and so on and so forth. So as long as world population keeps growing, and notice that curve, that trend in the curve is essentially exponential growth, which is the fastest growth possible for any function, any mathematical function. As long as world population keeps growing, this goal of sustainability is going to be elusive. There's another aspect that I want to draw your attention to, and it's the availability of energy. So this this image is a collection of pictures taken from satellites from different parts of the world and patched together into just one map. And from this sort of composite map, we can obviously realize that we're wasting a lot of energy, especially at night. But at the same time, the availability of energy is not equal for everybody. So if there's 8 billion people on the planet, there's a large fraction of humans that do not have any electrical power. You can wonder how many these are. Well, the estimates vary, but it's somewhere between 1.5 and 2 billion. So if it were 2 billion people, that would be about a quarter of the world population that does not have power at night, electrical power. In the best case scenario, they might be able to burn kerosene lamps, which is, of course, are not very healthy. And these same people who do not have electrical power, they typically will not have sufficient clean water and sanitation, and they will not have health care, they will not have enough food, and they will be typically living below the poverty line. Now, going back to the promise of solar, we can sort of invert this map and consider it a map of possibilities, because the same areas that are dark at night are the ones that actually have most sunshine during the day. And this presents a huge opportunity if we were to deploy large-scale solar technologies in these parts of the world, coupled with perhaps other renewables and effective storage solutions. We could drive very profound and unprecedented societal change within 1 or maximum 2 generations. This, of course, requires a major concerted effort. And this is why I, at some point about 10 years ago, I approached UNESCO. This is the United Nations Educational, Scientific, and Cultural Organization, because as you can quickly realize from what we've discussed so far, sustainability, and in particularly the energy challenge, it's not a simple scientific or technological challenge. It is much bigger and much broader. It is political and societal and economic. It involves population growth, which is something that we scientists cannot do anything about. And even from a politics and policy point of view, if we look at what happened in China, for many years there was the famous one-child policy. Then this policy was relaxed. This actually happened about the time, I think it was 2016, when I visited Professor Zhang at Peking University. And just around those days, the Chinese government had decided to relax the one-child policy. Because even though it managed to contain the population of China for some time, it created a lot of other problems. And so that is clearly not a simple solution to such a complex problem. So UNESCO has a program called UNESCO Chairs. These are essentially networks in which several organizations and institutions will pool resources to jointly address pressing challenges and contribute to societal development. Of course, these chairs and networks must work in areas that are prioritary for UNESCO, such as education, for example, and in general, they should also be addressing 1 or more of the Sustainable Development Goals. The chairs are designed to act as think tanks and bridge builders between academia, local communities, research, and policymaking. If you want, this is one of the reasons why I set up this chair, because my long-term goal is to inform and influence policy decisions. That's where we can have an impact which goes beyond sort of our typical academic impact. So what we would like to do is really see transformational policies concerning energy. In the meantime, one of the overarching sort of goals of the chair is capacity building. So training the next generation of scientists and engineers in the areas of renewables and sustainable energy. So the sort of overarching objective is to obtain access to sustainable energy for all. And we do this through research that is built on sharing knowledge in emerging energy technologies, renewables. So we basically focus on training, sharing knowledge, sharing expertise and know-how. We host visiting professors and students. We organize international workshops and educational activities. We offer web-based courses, and we train PhD students mostly, so sort of high-level training from countries in the South. We have a lot of confirmed countries, partners in about 20 something organizations in the South. So these are four of the main renewable energy technologies: hydroelectric, solar, wind, and tidal. Hydroelectric, wind, tidal, well, they're fairly mature technologies, and they're certainly not at a scale that I would be able or interested in doing research on. So our main focus in this space is solar. Well, let me give you just briefly an overview of the topics that are covered by the chair. I'm the sort of chairholder, as the, if you like, the coordinator of this network, but this involves many colleagues both at INRS and in the partner organizations. So we work on materials for energy saving. Energy saving will have to be a huge component of the energy transition because we need to buy time. The transition is urgent and we're not ready because we don't have the infrastructure for the energy transition. And so we have to buy time while we develop and build that infrastructure. Now, a few hundred years ago, we were mostly burning fire as the source of illumination. Then in the late 19th century, we started with the light bulb, the incandescent filament, which has lasted several decades. And then we're now in the era of solid state lighting, in which we use these light emitting diodes that have two huge advantages. One is significant energy saving, and the other is reduced CO2 emissions. So this is one great example of energy saving, but there's also others. If you think about it, many buildings that are still used today were built several decades ago at a time when energy for cooling and heating during the winter, cooling during the summer, was cheap. And so those buildings were made with materials that have very poor thermal insulation properties. So at this point, there's significant research efforts working on next generation materials with good insulation properties. And then from a sort of engineering and architectural perspective, a lot of buildings are sort of being coated with literally some kind of protective coat that provides effective thermal insulation. Another area that is quite important in renewables is energy storage. Now, you might think storage is important, for example, for the electrification of transport, such as electrical cars and whatnot. And this is absolutely true, but if you think about it, in reality, this is a sort of reverse problem in the sense that electrical vehicles are a good solution for sustainability only in as much as the electricity comes from renewables. From then the problem is just being shifted. It says Zoom has a problem. I don't know if I'm still. Oh,
we can see your screen.
Okay, sorry, because it says Zoom is not responding, and so I don't know if I'm. Okay, all right. It seems to be working, even though it's
you can log out
working.
and then log in. Okay, Rosei?
Want me to So I was saying that energy storage is a critical component for the electrification of transport, but this is only useful in as much as the electricity comes from renewables. So in fact, it's quite the opposite problem. Storage is the grand challenge of essentially all renewable energy technologies because renewables are intermittent. If you think about it, wind goes in cycles of half an hour. Tidal power, of course, depends on the tides. Now they're fairly predictable, but still they're intermittent. Solar energy is, in a sense, very intermittent. I mean, I can predict exactly night and day, but even during the day, if a cloud passes overhead, the power will drop dramatically, and you cannot predict how long this sort of drop in power will last. So this is why storage is so important, because the intermittency is such that we need to be able to effectively store the excess energy that is not needed now for later use. And of course, materials for energy conversion. Now, there's many technologies for energy conversion, depending on the source and the objectives. But as you can imagine, we are mostly interested in developing next generation solar technologies. So the challenge here is to absorb as many photons as possible from the distribution intensity that the sun generously sends to us, that the graph that you see at the bottom right, and convert them into another usable form of energy. In most cases, energy conversion processes essentially focus on converting some source into electricity. But of course, solar can also be used for other quite interesting purposes. You see that my video keeps turning off. So let's see if I can, okay. So we worked for quite some time on this sort of exotic concept of the bulk photovoltaic effect. Let me remind you first how a classical p-n junction photovoltaic device works. So basically, you have a semiconductor with a certain band gap, and the semiconductor is doped in one region with p-type doping, and another region in n-type doping. So what happens is this: the semiconductor has a band gap, and it can absorb photons with energy higher than the band gap, because you need that energy to have an electron from the valence band jump into the conduction band. So you only absorb photons with energy higher than the band gap. So the semiconductor absorbs photons, and this absorption creates an excited state in the system, which is called exciton. And the exciton is usually short-lived, of the order of femto, maybe picoseconds, more or less. And what happens is that the exciton splits into two charges, an electron-hole pair. Now, at the interface between the two regions, N and P, there's a space charge distribution, and this creates an electrical field. So this electrical field will drive those two charges towards electrodes. And so I measure a current, and that means that I've effectively transformed a photon, electromagnetic radiation, into electricity. So basically, this is the concept that is used in traditional commercial solar cells. We've been working, as I mentioned, on the bulk photovoltaic effect, which is a very, very different concept, in the sense that instead of having a p-n junction, which creates that electrical field that is used to separate charges, now we are using a ferroelectric material, which is sandwiched between two electrodes. So the top electrode is the transparent conductive oxide. So that's where the photons are collected. A ferroelectric is usually a wide bandgap semiconductor. So again, it will absorb all photons with energy higher than the band gap, and these will, as usual, create an excited state, and the exciton will split into two charges. And now a ferroelectric is a material in which there is typically a permanent polarization. that extends across the whole bulk of the material. So this polarization field can actually separate charges and drive them towards electrodes. Most of you have probably never heard of this concept, and the reason is this: it has some very severe drawbacks. One is that ferroelectrics are typically insulators, so yes, you can transform photons into charges, but the ability of this material to transport charges is quite limited. So typical current densities are the order of nanoampere per square centimeter. Also, as mentioned, a ferroelectric usually has a large band gap, which is 3 or 3.2 eV or more. What does this mean? Well, if you recall the distribution of the solar spectrum at higher energies, that's where you have the ultraviolet, and that portion of the solar spectrum is quite limited. Only about 4 to 5% of solar photons are in the ultraviolet region. So basically, by using a large band gap material, we're giving up on about 95% of usable photons. And this is a huge loss at the outset. There are some advantages. You don't need to form a p-n junction, and the total photovoltage is a series sum across grain voltages, so it can actually exceed the band gap. Now we started using multiferroics. This is a sort of subclass of ferroelectrics in a sense that also have magnetic properties. There's very few cases in which you can have combination of these properties, and that's because usually the energy levels are in competition. Typically in multiferroics, the band gap ends up being smaller because you need to have d-level electrons. Otherwise, you can't have both properties, and this tends to shrink the band gap. So, for example, bismuth iron oxide has a band gap that can range between 2.2 and 2.9 eV. Bismuth iron chromium oxide has a band gap that ranges between 1.4 and 2.5 eV. And bismuth manganese oxide has a band gap of about 1.1 to 1.2 eV. So you can see that these values of band gap are actually much smaller than a typical ferroelectric, and this means that these materials can absorb much more significant portions of the solar spectrum. So we showed the proof of concept more than 10 years ago, and this essentially was a preliminary prototype or test that showed that yes, we can use these materials as photoabsorbers, and they have not very high efficiencies, but started looking promising. But then we sort of serendipitously discovered a completely new concept that was quite interesting in its own right and helped us increase the efficiency by a lot. So if you look at these first devices, we had an efficiency of maybe about 1%. What does that mean? That's the power conversion efficiency. It's fairly low compared to standard commercial silicon panels, in which the efficiency is about 18 to 20%. So yes, of course, we're very far from anything that can possibly be commercialized anytime soon. On the other hand, you recall that in the early days of the bulk photovoltaic effect, the efficiencies were much lower, because if you have a current density of nanoampere per square centimeter, that means that your efficiency will be very small. Initially, the efficiency was of the order of 10 to the minus 7. Imagine that, 10 to the minus 7. It's totally negligible. So we bridged essentially 8 orders of magnitude from 10 to the minus 7 to 1%. And then we found that we can, this one first. We can tune the band gap in this particular material, BFCO, by varying the relative cation ordering of iron and chromium in the double perovskite lattice. We can actually tune and sort of shift the band gap. So depending on whether these cations are completely ordered or completely disordered or somewhere in between, then the values of band gap are different. So in the totally ordered case, we have a band gap of 1.4, which is actually a magic number in photovoltaics. That's where you have the maximum power conversion efficiency according to the Shockley-Weisser theory. And so this means that we can grow films with different cation ordering that have different band gap and therefore different absorption properties and ultimately different efficiency. And we can also grow the films epitaxially, one on top of the other, so that we can start with the material that has the smallest band gap and then progressively larger and larger, and that enables the maximum absorption of solar photons. So if we go back to this slide, essentially we varied the cation ordering, which varies the band gap, leading to 3 different single layer films in which the efficiency varies between 0.7 to 2.5 and 3.9%. And then if we grow them epitaxially one on top of the other, they have exactly the same crystal structure and lattice parameter. The only variation is this cation ordering. Then we reach the this record value of 8.1%, which starts to get pretty close to double digits. As far as I know, this is still the world record of power conversion efficiency in ferroelectric photovoltaics. Of course, we still, even after years of working on this, there's still a lot of optimization to do. As you can see, the fill factor is not very high. This means that there's significant losses, optical and other, in the device. So this calls for devices that are sort of higher performance just in the way that they're engineered. We also showed at some point that we can grow BFCO directly on silicon, and this paves the way towards a technology that enhances current silicon photovoltaics instead of competing with it. We also looked at another material, which is a combination of bismuth manganese oxides. So there's 2 distinct phases in this composite material, BMN03, which is ferroelectric, and BMN205, which is semiconducting. So we grow these on niobium doped STO, which is a typical substrate for the growth of perovskite oxides. And then we use indium tin oxide as our transparent conductive oxide. Now, in all these cases, BFCO and BMO, the film thickness has to be pretty thin, of the order of 100 to 200 nanometers. You don't want to have thick films because the further the charges have to travel when you split the electron hole pair, the higher the chance of losses, because 2 charges of opposite sign will recombine and that will be a loss, or they can be quenched by defect. So you want to keep that distance, that thickness, as small as possible. One of the advantages of some of these materials is that they have a high absorption coefficient. So even thin films of these materials are able to absorb a significant amount of photons. So in this case of the mixed phase, we end up with an average power conversion efficiency of about 4%. So it's not quite the 8% of the other material, but recall the other material is a multi-layer. This is a single layer. So our champion device has a 4.2%. And again, this requires more optimization. We were able to extract the current density both from the external quantum efficiency and by extrapolating from IV curves, and it's roughly 7 point something milliampere per square centimeter, which is fairly decent. We were also able to estimate the band gaps of the 3 different cases. So of course the high performance photoabsorber material is the composite one, but we also compared with BMN03, the ferroelectric, and BMN205, which is the semiconductor. As you can see, the three have very similar values of band gap. And yet, when you compare their performance in terms of photoabsorbers and photovoltaic materials, then the difference is striking, because the pure semiconductor BMN 205 has a power conversion efficiency of 0.000014, which is pretty much negligible. The ferroelectric BMN 03 has 0.11, which is very low, but actually respectable within this category, this class of materials. And the best composite film reaches 4.2%. So you really need both phases to obtain this effect. Again, we have fairly low values of fill factor. Again, means we need to optimize several aspects of the device to reduce losses. Why do we need both phases? We interpret this phenomenon in terms of grain boundary barrier potential that sort of enables charge transfer between the different phases. And so this is why you need actually two different phases. One is not effective for this purpose. Now, so far so good. We had a lot of fun actually working on these exotic materials. Many of you probably have heard of hybrid organohalide perovskites. Many of you maybe even work on it, and those are essentially very popular these days because this class of materials, organohalide perovskites, have reached very, very high efficiencies. I'm not even sure what the world record is now, probably 25, 26%, something like that. This is more of a niche, and even though our efficiencies are much lower, we have a tremendous advantage over the organohalides because our materials are inorganic oxides and therefore extremely stable, whereas organohalide perovskites are known to have severe stability issues. So the devices made with those materials typically do not last very long. Now, in parallel to what I just showed you, we started working on photoelectrochemical solar cells that essentially mimic the photosynthesis reaction in plants. And the reason why we do this is that we want an alternative which is low cost to whichever exotic or even commercial technologies that already exist. You're going to say, okay, but silicon solar cells are not that expensive, and that's true. But there's another advantage of these types of materials and processes. They're not only low cost, they're low energy intensive. And this is an important aspect of the energy transition, that we need to develop materials, technologies that do not require large energy input for their fabrication, because today that energy input will mostly come from fossil fuels, and this means that during the transition, we're going to cause substantial carbon emissions. So the prototype technology here was invented by Michael Gretzel some 30 plus years ago. Dye-sensitized solar cells, in which you have a photoabsorber made of a metal oxide, like titanium dioxide or tin oxide, zinc oxide, iron oxide. This tends to be quite stable. It also has a large band gap. So essentially, its ability to absorb and convert solar photons is limited. So you need to sensitize it with something else. In the original invention, it was dye molecules that absorbs in other regions of the solar spectrum. This technology has reached its peak efficiency in the lab of about 14%, as far as I recall. Stability is also an issue. They're actually more stable than the perovskites that I mentioned earlier, but still, they do not last 30 years like silicon solar cells. Now, we and many others replace those dye molecules with quantum dots. These are semiconducting nanocrystals in which you can actually bias tune the band gap by changing the morphology, the composition, and in fact the size and shape of the material. And they're quite easy to make, much easier than dye molecules. And also they're low cost, and their fabrication is low energy intensive. Okay, we're going to skip this. Now, you can use these quantum dot solar cells for direct conversion into electricity, but you can also use them for another purpose, which is hydrogen production. You may have heard of hydrogen as a clean fuel because when it's combusted in a fuel cell, its only byproduct is water. Now, there's three challenges that need to be addressed for a hydrogen economy to take off. One is production of hydrogen. Where do you extract it from? In the atmosphere, its composition, relative composition, is only about 1%. So that's a bit of a problem. You can't dig it out of the ground. Storage is an issue because H2 is the smallest molecule on this planet, and storing it effectively is not easy. And its combustion, yes, it's the only byproduct, as I mentioned, is water. But on the other hand, well, it requires electrocatalysts made of platinum, which are rare and expensive. So we mostly focus on hydrogen production, and we're trying to extract it from water. In fact, so far, hydrogen is mostly extracted from methane, natural gas, CH4, which is a non-renewable feedstock. And so in this sense, it's not exactly a win-win solution to extract a clean fuel like hydrogen from a non-renewable source like CH4. Since 2/3 of the planet are covered in water and the only byproduct of combusting hydrogen is water, this could be an environmentally clean and friendly cycle. But the problem is that this water splitting reaction is an exothermic reaction, which means you need more energy to split up the water molecule than what you retrieve when you combust the hydrogen. So you need some sort of free energy to make up that differential, and that free energy will come graciously from the sun. So this is the concept. We use those quantum dot cells as electrochemical cells for water splitting. There's three major processes that are involved in this reaction. One is light absorption by the semiconductor, the photoabsorber. We discussed this already. It's the same concept as in a solar cell. The electron hole pairs are separated and transported, similar to a solar cell. And then instead of being collected at electrodes, they actually have to reach a surface where water molecules are absorbed, and that's where the redox reactions occur and split the water into oxygen and hydrogen. What are the requirements for the photoanode? Now, we know that the energy required to split water is 1.23 eV. So you imagine, okay, I need a band gap of 1.23 eV. Well, it's not that simple. There's going to be thermodynamic energy losses, and you need an overpotential for the surface reaction. So basically, you can be sure that your band gap has to be a little bit larger. The minimum is about 1.8 eV. You need a semiconductor that is efficient at separating and transporting charges. It should be stable and have a strong catalytic activity. And then you would also want it to be made of low cost and earth abundant elements. So a lot of conditions right there. So it's not simple at all. So titanium dioxide, I think I mentioned, it's one of the oxides that is mostly used as the main component of a photoabsorber. And it has a large band gap, as mentioned. It's inert, resistant to corrosion, non-toxic, reacts under mild operating conditions, and has a high oxidative power. So these are all pretty major advantages. Okay, we can skip this. And we typically sensitize it with quantum dots, and in particular, we use giant core shell quantum dots. So instead of sort of regular quantum dots, they're made of one single phase or composition. We designed and synthesized entire libraries of these giant core shell, in which you have a core of one material and a shell of a different material. And this really enables, it gives us the opportunity to fine-tune the optoelectronic properties and it's done by wet chemical synthesis, which again is inexpensive and low energy intensive. So this is a typical quantum-based photoanode in which we use giant core shell quantum dots. They tend to be more stable, less sensitive to surrounding chemical conditions. Their band alignment is tunable by tailoring core size and shell thickness, and also the sort of composition, whether it's gradient composition or uniform composition, so on. Now, the absorption range, unfortunately, is somewhat limited, and the thick shell can actually limit the efficiency of charge transport. So this is how it works. You basically have dissociation of the photo-generated excitons at the quantum dot oxide interface. Electrons are injected into the TiO2, transported in the mesoporous film, collected at the front electrode, transferred to the platinum counter electrode, and that's where hydrogen generation takes place. We're mostly focusing on this half cell, so we're not working that much on the oxygen evolution side. So for simplicity here, we use hole scavengers in the electrolyte that provide shuttle transport for the photo-generated holes, and essentially this also helps to maintain the stability of the device. So we obtained several records of photocurrent density and hydrogen generation, and this is one example: 11 milliamps per square centimeter and 110 milliliters per square centimeter per day. So quite encouraging results. One of the issues, though, was that you can see here core of lead sulfide, shell of cadmium sulfide. These quantum dots contain both lead and cadmium that are quite toxic. So this is another obvious issue. I'm going to skip this. This leads us to consider Sustainable Development Goal number 12, which is responsible production and consumption. If ever you haven't seen this yet, it's quite interesting. On the left, the periodic table of so-called endangered elements. What this means is that many key elements that are used in a lot of technologies are increasingly scarce. And so if we want to avoid or prevent bottlenecks, we need to integrate recycling principles into the design and fabrication of new technologies, as well as develop biodegradable technologies and focus on low energy intensive technologies. So here we move to a different type of material in which the end result, the core shell, is copper indium selenide, copper indium sulfide, which are mostly considered non-toxic. The precursors still contain cadmium, so it's not entirely green, but at least the end result is green. So that's actually pretty decent from that point of view. And there is, however, a sort of trade-off, because yes, the device works and it works reasonably well, but the photocurrent density is actually much lower, 3.1 milliamp per square centimeter. So we gain from one point of view of using materials that are non-toxic. We lose from another point of view in terms of performance. Another aspect that is really crucial in these devices for water splitting is the fact that you need an electrical field that will separate those charges. And applying an electrical field obviously costs energy. So one way to address that is to embed in the photoanode material something that already has a built-in electrical field. So again, that can be a ferroelectric. So the proof of concept is right here. We mixed barium titanium oxide, which is a typical ferroelectric, with the TiO2. And we used this hybrid photoanode to separate charges, and this reduces the energy input in the device. So it's quite effective. Another technology that we've been working on, and don't worry, we're nearing the end at this point, are luminescent solar concentrators that personally I prefer to call solar windows. It's kind of simpler. So imagine you have a large and tall building and you want to use the area of your windows to collect solar energy and transform it into electrical power. Well, if you use standard commercial silicon solar cells, that's not going to work because they're not transparent. So you need something that is transparent, completely different concept. So here what we do is we basically build a planar waveguide made of a transparent polymer. And within the waveguide, we embed chromophores, or if you like, sort of antennas, that will absorb a solar photon at one wavelength and then re-emit it at a different wavelength. Then the re-emitted photon can travel through the waveguide, and it will reach the edges of the waveguide where I will have placed long and thin solar cells, could be silicon solar cells, whatever, it doesn't really matter. And so those re-emitted photons will actually hit a solar cell and be transformed into electrical power. Of course, the power generated by one such window is limited, so you need to have many windows, and that's why this works quite well for building integrated photovoltaics, essentially high-rise buildings that are very tall and very large. Now, one of the critical elements of these antennas or chromophores is that they need to have a large Stokes shift, which is the difference in wavelength between the absorbed and the re-emitted photon. And it turns out that, again, these core shell quantum dots are quite effective because, again, by varying the core and shell and relative thickness and composition, we can really obtain a very large Stokes shift. Yet again, our initial materials were made of lead sulfide and cadmium sulfide. And then we went through successive sort of iterations of greener and greener materials to the point that our latest generations of dots are carbon dots, mostly made of carbon with a little bit of residual nitrogen, oxygen, and hydrogen. So these are actually the four most abundant elements on the planet. So this is excellent from a sustainability viewpoint, and generally these elements are considered non-toxic, although of course nanocarbon could be toxic as well. So there's always an open question mark. Anything nano could easily be toxic, even though its bulk counterpart might not be toxic. So I shared with you a little bit of our work on nanostructured materials. We basically use them as building blocks in emerging technologies. We try to vary structure and composition and optimize properties for various applications. And our focus has been for quite a while on renewable energies, in particular solar technologies. So I shared with you a lot of work initially on ferroelectric photovoltaics, and then now we have mostly shifted to quantum dot solar technologies, including photoelectrical, hydrogen generation, and solar windows. I wanted to briefly share this sort of professional development course that I created with a colleague about 20 years ago. And another colleague and I co-authored a book by the same title of the course, Survival Skills for Scientists. And I also published a few articles in the journal Materials Education. The course was quite successful. We've given it in Montreal many times and also all over the world. The book was also quite a hit, and it was even translated into Japanese. So there's a version of my book that I cannot even read. I also wanted to mention I had the great honor of launching a new journal quite recently. So I'm the founding editor-in-chief of RSC Applied Interfaces. So very soon we will welcome submissions. I hope many of you will consider submitting to our new journal that I'm quite excited about. And I wanted to mention I recently moved from Canada back to Italy, which is where I was born and grew up. So I am in the city of Trieste in the northeast of Italy. It's a beautiful city on the Adriatic coast, as you can see from some of those pictures. And Trieste is was actually elected by the Euroscience Open Forum as the European Capital of Science in 2020 because we have many cutting-edge research institutions in such a small city. And I owe a debt of gratitude to the funding agencies that supported us for the past 20 plus years. Now here in Italy, I have to start over. But anyway, I'm grateful to all the funding we received from industrial partners and the province of Quebec and the federal government of Canada and other sources. And I'm mostly grateful to the students and trainees that worked in my lab, almost 200 of them from 46 different countries. And 30 former group members, 30 alumni, are now themselves professors in 14 different countries. And with that, I would like to thank you and conclude.
Thank you very much, Professor Rosei, for this wonderful talk. And it's right on time. So I really appreciate that you starting with your view in UNESCO, and that's I introduce you as well. And also you're covering a wide range of the solar technologies and to address the energy challenges. Yeah, that's wonderful. So probably I think it's a time for us to introduce our panelists tonight. And we're looking for wonderful discussions. Probably you can stop sharing your slides soon. And our first panelist today is Professor Francisco Stalaci from EPFL, Switzerland. And Professor Stalaci actually leading a supramolecular nanomaterials and interfaces laboratories. So welcome. And also today, our second panelist is Professor Rushen Yang from Xidian University in China. And Professor Yang is currently the Vice Dean of the School of Advanced Materials and Nanotechnology in Xidian. And his work is on bio-inspired functional materials and energy harvesting technologies, and has been recognized by with NSF Career Award, etc. And welcome, Rushen. And tonight we also have our ex-challenger is Shi Wei from Australia National University, and she's currently a PhD candidate in electronic materials engineering, supervised by Professor Lan Fu, and who is actually our friend for the INRS. And Shi's research interest is focusing on 3.5 semiconductor nanowire-based gas sensors. So now let's welcome all of the panelists on the stage to discuss. And as usual, our first turn is for our ex-challenger. So Shi, the stage is yours.
Okay, thank you so much. Thank you so much for Professor Chen's introduction. And thank you so much for Professor Rosei's wonderful talk. And it's very inspiring for me because I basically have no idea about this research field, but I learned a lot today. So thank you so much. And I have two questions about you. So since I have no background in this field, so I want to ask for the bulk photovoltaic material you mentioned. I wondered if you can expand a little bit about the principle that how exactly can the light convert the polarity of this structure. And the second question is about the device you make. You mentioned you have managed to convert the efficiency from minus 10 to minus 7 to 8.2%. So because you use the epitaxial growth method to grow a few layers of this kind of material to get to avoid the mismatch of the lattice grain. So will this increase the manufacturing cost? Because we have the same issue in the photovoltaic semiconductors. So how can you avoid this drawback with this performance improving? So that's all of my question. Yeah.
Okay, thank you. Thank you very much. Interesting question. So the first question, so I think maybe I didn't explain it very well, but essentially instead of a sort of traditional semiconductor like silicon, you're using a ferroelectric. And now ferroelectric has a large band gap, and so it only collects photons from the ultraviolet, and there's not many photons there. Anyway, the advantage of the ferroelectric is that you don't need a PN junction as you do for a traditional semiconductor. The PN junction plays a role of creating an embedded electrical field that separates charges. Now, if you have a ferroelectric, there is the depolarization field that carries across the whole material. And so this field will separate charges. It doesn't really interact with the photons. Its only purpose is to separate the charges. So hopefully this answers your first question. Now, your second question is, yes, by changing sort of type of ferroelectric, so instead of a traditional ferroelectric like, say, barium titanate oxide, which has, again, a large band gap, we're using these multiferroics that have a smaller band gap, and therefore already by having a smaller band gap, we're absorbing a lot more photons because we're not limited to the ultraviolet. We can collect photons from the visible and infrared. Now, one huge drawback, which you correctly pointed to, is the manufacturing of these materials. I didn't go into detail because, of course, there's only so much I can say in a presentation like this, but we grow them by pulsed laser deposition. This is a plasma-based material synthesis approach, which is extremely effective in the sense that plasmas can reach far from equilibrium synthesis conditions that nothing else can achieve. And so for certain complex phases, for certain very accurate types of synthesis, these plasma-based approaches, in particular pulsed laser deposition, are perfect. But of course, this is okay for fundamental research, but the sort of TRLs, the technology readiness levels of this kind of research, are going to be fairly low, unless you look at some niche applications. I mean, you can think of all sorts of niche applications in which cost is possibly not such a huge issue, and then you can actually commercialize them. I actually enjoy working with the aerospace industry because they don't really care about the cost. And that's because, when you launch a satellite, the main cost is the launch of the satellite, which is millions of dollars or euros or whatever. So if you add to the satellite some kind of device which costs $100,000, but which doesn't make the launch more expensive, or maybe reduces the volume and weight of the satellite and therefore reduces the cost of the launch, then it's actually welcome. Of course, this is not amenable for large-scale applications and for large-scale commercialization. And that's why we moved to the quantum dots, because we realized that there were too many drawbacks from a manufacturing point of view. We couldn't think of a sort of easy scale-up process that wouldn't be very expensive.
Thank you so much, Professor Rosei.
Thank you. So, Zhiyu, we now probably move on to Professor Francisco Stellasi. Probably you want to have some questions and comments for Professor Rosei's talk.
Absolutely. So I'll start with a comment that all of this is an impressive array of quite successful technologies that have been developed by our lab. And I will continue instead in terms of question to go further on the ferroelectric photovoltaics. It's all very promising for two reasons. One is these are very stable materials. And if we have to install photovoltaics throughout the world, we want things that last a long time. Because if not, we're going to waste a lot of energy in producing, fixing, or recycling them. But the efficiencies you are now, they're very far from what other technologies can offer. Where do you think you can get to with this technology? What is reasonable?
There are some estimates in terms of the theoretical limit for ferroelectric photovoltaics, and we're far from reaching those theoretical limits. Now, if you recall, I highlighted the fact that our fill factors are quite low. You know, you want to have a fill factor which is like 70-something%, and we have less than half of that. So this means that, you know, there's a lot of losses, optical losses and whatnot. We think we can probably double those numbers, but that would require substantial improvements in device engineering and in materials quality and so on. Having said that, I think I also mentioned at some point that we managed to grow BFCO, which is our champion material, epitaxially on silicon with a buffer layer of magnesium oxide. And so, you know, if you take a silicon solar panel that has a power conversion efficiency at 20%, and you add this kind of material, and you only need a very thin film, and you increase the efficiency by 1%, you can quickly calculate that that small increase in efficiency from 20 to 21% has a huge economic impact. So, you know, you can also look at it that way. Instead of creating a competing technology, you can try to, at least at the beginning, try to enhance an existing technology like silicon, which is already mature, stable panels that last 30 years and so on.
If I can ask a follow-up question. For photovoltaics, there is the Shockley-Carey limit, which is the theoretical limit of conversion. Is there any such thermodynamic calculation for ferroelectric photovoltaics?
I didn't see anything published, but you can sort of quickly estimate, and it's 30-something% like silicon. It's not very different. It really depends on the band gap also in that case. So, you know, if you have materials with reasonable band gap, you can have a fairly high theoretical limit.
Okay, thank you.
So, as I mentioned, we're far from any estimated limit.
Okay, so very nice. Do you have any further questions, Francisco?
No, I'm okay. Thank you.
Okay, great. Thank you. And now, Professor Lushan, it's your turn.
Sure, thank you. Congratulations, Professor Rosei. That's really a very wonderful talk. I'm really enjoy it. And I do, you know, just like a few others, I'm very interested in your ferroelectric solar cell. You know, I also personally I also work on the piezoelectric materials and ferroelectric material and also applications. And you also mentioned one advantage of the ferroelectric photovoltaic technology is that the output voltage is not limited by its band cap, and theoretically it could be even go beyond the band gap, right? So, you know, that's really nice. But however, when I check your the champion material BSCO, so that you have the world record performance, but the voltage is still only around 0.6 to 0.7 volt. So what's the reasons why the voltage is not as high as we expected? What prevents it from being any higher? So what's so what's the reason for that?
That is a great question, and honestly, I wish I knew the answer. I mean, this has been a headache for us because, yeah, as you highlighted, and I said it before, in principle, you can obtain an output voltage which is higher than the band gap. And this is one of the reasons why the bulk photovoltaic effect is also called the anomalous photovoltaic effect, because it's quite an anomaly to have an output voltage larger than the band gap. And instead, we have something which is smaller. I don't have an answer for that yet. I wish I did, but It's not something we have figured out as yet.
Okay, great. Yeah, probably if we can figure it out, maybe we can go, much beyond and maybe even double your performance, right? Because you said we are well below the limit.
Yeah, we're well below the limit. And I mean, I pointed to the fill factors being low, but you're right. Also, the output voltage is low. And so all these aspects point to the fact that in principle, the overall performance, including the power conversion efficiency, could be quite a bit higher. I mean, we're not going to increase it by another order of magnitude, obviously, but we could increase it by maybe a factor of 2 at some point if we manage to
kind of double. So I think that should be doable, right? Yeah. So probably later, when you visit CN, we can have a further discuss on the piezoelectric part, the ferroelectric material. Here, I'm also have some question about your another photovoltaic, the luminescent solar concentrator. The reason it catches my attention is it's really colorful, right? Very beautiful, all those glasses. So for that one, but I also got some question from your schematic diagram. So the light, come to the film, and so it will be scattered by kind of maybe the quantum dot or whatever material in the film, and start transmit laterally as a waveguide, right? And go to the edge. But I think when the income light is perpendicular to the surface of the film, I would imagine most of the light may, intended to transmit through the film, right? Probably only small portion, travel laterally. If this is the case, will that, theoretically make your efficiency cannot be high? So kind of, I become not quite familiar with this type of photovoltaic. Could you be, give us a little more detail on this one?
Right. So you're certainly correct. I mean, there's a trade-off, right? So you have your waveguide that is placed in front of the window, and so you want a lot of light to go through, because if you sort of use a substantial fraction of that light for other purposes, then you will lose illumination in your inside your building. So you want to capture a fraction of those photons without substantially reducing illumination, and then the fraction that is captured is sort of re-emitted by whichever chromophores. In our case, it's quantum dots, but again, you can use dye molecules or something else. So this is obviously another limitation in the overall sort of efficiency of power conversion of this solar window device. There's not much that can be done about it. I guess, again, the main advantage of this concept is really when you have a very tall, a very large building, and in such a case, you could place solar panels on the roof, but that's a very small area on the roof, right? I mean, as large as the base of the building can be, that area is going to be small. So instead of looking at that area, you take all these solar windows. You can calculate depending on how tall it is and how large it is. You can just sum them all, and then you get a decent sort of electrical power output. But there's not much that can be done. I mean, if you absorb and convert too many photons, you will lose in terms of internal lighting.
Yeah, that's true. Definitely for this one, we find need, depending on the need, you have to have some compromise. You either get a bright, room, or you got more electrical energy from the film, right? Yeah. Thank you. So probably that's all questions I have at this moment. And
Great.
Thank you.
Yeah, I think you guys have a really hot discussions with each other. So as a moderator today, I feel that I noticed that Professor Rosei's background, you started with quite sort of trained in physics with a lot of fundamentals, and then starting to switch the gears to many of these kind of applied topics. So could you share with us your views from the more kind of fundamental trainings to and then apply to this kind of applied topics? Because we have a lot of graduate students currently as the audience here. So probably share some of your thoughts.
Sure. I'm still very passionate about some parts of my research program, which are quite fundamental, and even the sort of the materials that the topics that I shared today. The TRLs, the technology readiness levels, are fairly low. I mean, we're not going beyond 4 or 5 years, so they're still fairly low, which points to reasonably fundamental research. There has been a tendency worldwide for the past at least 2 or 3 decades to push more research towards applications, even in academia. And this is something that, philosophically, I'm very much against this idea, because that's not the role of academia. The role of academia is really to train people, to train the next generation of students, scientists and engineers, and then these highly skilled people will join the workforce, private companies that want to commercialize whatever. Sometimes it can be national labs, you name it. But our mission, our core activity should always be to train. And of course, there can be a component of applied research, but the greatest innovations almost always inevitably come from fundamental research. So I really want to encourage the younger generation now to have the sort of the guts, the courage to continue exploring ideas that derive from their curiosity to discover how the world works, and not necessarily focus only on applications. Curiosity-driven research has given tremendous fruits. The only, of course, drawback is that usually you have to wait a while before those discoveries bear some fruit, and you cannot predict what kind of innovation will come from them, and you cannot predict when it will come. But for example, it took about 100 years to go from Einstein's theory of relativity to GPS technology. But today we cannot really live without GPS technology. It took about 100 years, and nobody could have predicted it. It took a while to go from NMR spectroscopy to magnetic resonance imaging. And now that's a fundamental diagnostic tool that is used in so many hospitals and saves a lot of lives. But the scientists who invented NMR spectroscopy were not considering biomedical imaging. They just wanted to learn the structure of atoms and molecules. And there's so many examples like this. I mean, there's so many examples of some kind of fundamental discovery that later became a huge innovation that has an unprecedented societal impact, and that could have not been predicted at the outset. So I really want to encourage the younger generation to, follow your curiosity. And sure, you'll need a job at some point. You'll need a paycheck, and you'll need to compromise. I mean, you've seen how I evolved, and that's because in the Canadian funding system, there is a focus on university-industry partnerships. So if you don't engage with industry, you're not going anywhere. You will not be able to draw substantial funding and actually set up a competitive research operation. So I did it initially out of necessity. I also learned a lot, so I don't regret it. And in any case, like I said, if you look at my output, I have more than 500 papers and only about 4 patents. I still mostly do the fundamentals and not so much the applications. So at the end of the day, each one of us has to find the right balance and the right sort of trade-off of what is acceptable and interesting and stimulating, so that we can keep doing our job and be happy about it.
Yeah, thank you very much. I think that's definitely very, very informative for a lot of the audience today, like the curiosity-driven research. So that's about today, and we have such a nice time tonight, and I hope everyone here also have it. So it's time to wrap up, and thanks again for all the wonderful talks and discussions tonight. And especially we want to thank Professor Rosei. Let me actually represent the INRS to share with you the e-certificate. Could you see my screen?
Yes.
Yeah. So basically, this is actually the INRS. Basically, I represent the INRS to present this electronic certificate to show all of our appreciations for your wonderful talks. And also, we hope like someday we will be able to see you in person. And I think March is also a interesting time because you mentioned that on the March 1st, you moved back to Italy. I think that's a good memory for you. So as a little advertisement for the next week, INRS Talks 135. Basically, we're going to have Professor Andrew Alou for the talk, Extreme Control of the Light and Sound with Metamaterials. So please stay tuned. And for now, thank everyone and good night.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望